So the fact that our discussions about centripetal ideas involve both forces and acceleration, really lead us to using F equals ma, and that is certainly going to be our approach in these problems. Although once in a while, things like energy do show up as well. Um, so when we're using F equals ma, of course, we have to be very careful about the um, the direction of our forces as to whether certain forces are positive or negative, whether we have to break them into components and so forth. In these sorts of questions, you'll want to choose as your positive direction the inward direction. So you'll imagine a snapshot of the object, and you'll draw diagrams, of course, of the forces. And the forces that point inward will be considered positive, and the forces that are outward will be considered negative. So, like for instance, if we have a situation like this where we have a circular path and the object is at the top of the circular path of a vertical circle, here the gravitational force will be positive. But on the bottom circle here, when the object is at the bottom of that circle, now your weight force would be considered negative because it's pointing against that inward direction. So inward is going to be our positive direction because that's the direction of the acceleration. So certainly free body diagrams are going to be very important. Make sure that you are accurately labeling all the forces, but make sure you don't put forces in there that are forces that the object exerts on something else. You only want to have the forces that are actually being exerted on that object. And then take a look to see if the problem is asking about speed or radius. And in that case, you'll want to substitute the v squared over r expression for the acceleration. And sometimes our forces involve mass, like sometimes we'll have a frictional force or we'll have gravitational forces. And so look for situations where when the mass is not given, that perhaps it cancels out. Let's take a look at a couple examples here. This question is asking about the apparent weight of this person on a Ferris wheel. And so this represents just a rough sketch of that Ferris wheel. The apparent weight is referring to the normal force. That's actually how we experience our weight. We can't feel gravity, but if the ground is pushing on us, that gives us our sensation of weight. So the normal force is what this problem is talking about when it asks for the apparent weight. So let's go ahead and draw some forces on here. So this is our 60 kilogram person, of course, has a weight pulling down, and then sitting on that seat, the seat would push up. That would be our normal force. So in this case, because inward is actually the down direction, we would consider mg to be a positive force and then subtract the normal force. And since the problem does involve speeds and radius values, not just accelerations, we'll go ahead and put in that v squared over r expression. And then as we work our way through here, solving for the normal force, plugging in the various numbers that we were given, we find that the normal force is 540 newtons, which is smaller than the actual weight. Turns out that is 588, just the 6 times 9.8, or 60 times 9.8. So at the top of the Ferris wheel, this person feels lighter than usual. Actual weight is still 588, but the apparent weight, due to the normal force, is a little bit less. You feel like you kind of rise out of your seat. Okay, well, what if we look at the bottom instead? We'd expect this to be heavier. If you've been on a Ferris wheel, you can feel that you feel heavier when you're on the bottom part of the ride. So how does our setup change in this case? Well, our forces are the same, except that now the weight force points outward and the normal force points inward. And I've adjusted the size of my arrows to kind of represent that. There would have to be a bigger normal force now than weight force so that the net force would point upwards. Again, that is the inward direction for this snapshot. And so when we set this up with our F equals ma, it has a lot of similarities to the previous question. Really, the big difference is that our normal force is positive and our weight force is negative. Normal force is in the direction of acceleration, and the weight is in the opposite direction. And so as we work through our algebra, we end up adding our two expressions, our two terms, instead of subtracting, and we get a larger value than the regular weight or the actual weight. And so that corresponds with our feelings that we feel heavier at the bottom of the ride.